today we are discussing about quantum mechanics. So first of all, right, we must know what is atomic orbital. So I think you're all quite familiar with this diagram. It's an s orbital with here. So here's inside over here there is a nucleus. So an orbital is a three-dimensional region in space around the nucleus. So 3D around the nucleus over here, where there is a high probability of finding an electron. Can be here, anywhere. Okay, around this region. Next, what is quantum number? By using hydrogen atom as the example, an atomic orbital is specified by 4 quantum number. So the first one is principal quantum number, represented by n, indicate the energy level of the electron. Second one is angular momentum quantum number, represented by L, indicate the shape of the orbital. And then number 3, magnetic quantum number, represented by M, describe the orientation of the orbital in space. And then the last one is electron spin quantum number, S, represent the spin direction of electron on its own axis. Let's look at the principal quantum number n. The value of n determines the energy of an atom orbital, and thereby the energy of the electron in that particular orbital. So normally it started from the n equal to 1, 2, 3 until infinity. So if you notice, right, besides energy, the orbital size getting increased when the n value increase. So you can check based on this diagram, right, the size of 1s, 2s, 3s, 3s is the largest one. So the size of 3s bigger than 2s. Then next, what is angular momentum? Number L. Actually, it has others name, which is azimuthal subsidiary orbital quantum number. So the L actually is the integer 0 to n minus 1. So this angular momentum indicates shape and type of orbital. So since this formula, right, we know that n determines the L. So for example, when n equal to 1, L equal to 0. n equal to 2, L equal to 1 and 0, because from 0 to n minus 1. And then n equal to 3, 3 minus 1 equal to 2, so from 2, 1, 0. So this is angular momentum quantum number. If L equal to 0, right, actually got a meaning is represent s orbital. So can be 1s, 2s, 3s, so spherical. If L equal to 1, represent p orbital, which is dumbbell shape. Okay, 2px, 2py, 2pz, there are 3 orientation. This one is related with the next quantum number. Next, what is magnetic quantum number? Represented by M. Actually, right, the magnetic quantum number represents the orientation of orbital in the space around the nucleus. So the M integer is from negative L through 0 to positive L. So L determines M. So number of possible M value actually, right, the total number is, can apply this formula to L plus 1. So for example, when L equal to 0, M sure is equal to 0. You try to substitute 2 times 0 plus 1, so there is 1 orientation, so 1 M value. So one possible orbital, so it's S subshell. If L equal to 1, so 2 times 1 plus 1 equal to 3, so there are 3 possible value for M, which is negative 1, 0, positive 1. So 3 possible orbitals, so means this one is P subshell. And then if L equal to 2, M equal to negative 2, negative 1, 0, plus 1, and plus 2. So there are 5 possible orbitals, so this is D subshell. Each allowed combination of n, L, M values specify one atomic orbital. Size for n, shape for L, and then spatial orientation is M. So we try some example. If 2s subshell, right, means n equal to 2. So L, S orbital, so is equal to 0. So M equal to 0, 1 orbital. So 2p subshell, n equal to 2, L equal to 1. Why? Here, p subshell. So L equal to 1, so these are the M value, so there are 3 orbitals. And then 3 subshell, n equal to 3, and then L equal to 2, so these are the M value, so there are total 5 orbitals. So let's look at the details for s orbital. Spherical shape with nucleus at the center, 2s orbital larger than 1n. This is what we know because the n when n larger, right, the size bigger and then the energy higher. So electron farther from the nucleus only have one orientation, L equal to 0, M equal to 0. And then when L equal to 1 is p orbital, so get pux, py, pz due to the m angular momentum magnetic quantum number is from -1, 0 and +1. So as n increase, the p orbital getting larger, same concept as just now. So all p orbital have a loop at the nucleus. So along the z-axis, lie on the z-axis, so this is px, lie along the x-axis, px, lie along the y-axis, so py. Next is shape of d orbital. Shape for d orbital have 4 loops perpendicular to each other. One d orbital has 2 major loops along z-axis and a donut-shaped crater at the center. So when L equal to 2, these are the m value. There are 5 orbitals. So the name of the 5 orbitals are dyz, dxz, dxy, dx square minus y square, and then dz square. So when L equal to 2 is d orbital in cloverleaf shape, and then you have to learn how to draw the SPD orbital. So this one you can watch my another video, drawing of SPD orbital. So point to remember, we must always remember actually n limits L and L limits M. So these are the possibility when n equal to 2. So possible L value 0, 1. So you have to specify again when L equal to 1. So the m value suppose this 3. So there are 3 orbital. And then when L equal to 0, these are the m value. There are only 1 orbital. So maximum number of electron we can using this formula 2n square. So we try this one, 2n square. So 4, 4, okay, 2, 2, 4, 4 times 8. So there are 8 electrons. Why there are 8 electrons when n equal to 2? So let's check. So 1, 2, 3, 4. There are 4 orbitals. Each orbital 2 electrons. That's why the answer is 8. Again, 2, 2, 4. 4 times 2 equal to 8. Why 8 electrons? Because 1, 2, 3, 4. There are 4 orbitals. Each orbital can place 2 electrons. The last quantum number is electron spin quantum number, represented by S. This one indicates the motion of an electron. Either it's clockwise or anti-clockwise. If clockwise, positive half, anti-clockwise, negative half. Check this one. So when n equal to 1, L equal to 0. So the shape is 1s. So the m value is 0. So with positive or negative half electron. So here only 1 orbital, meaning that maximum 2 electron. So we check for 2. If L equal to 0, 2s. If L equal to 1 is 2p. So these are the m value. So these are the s value. So over here there are 1 orbital. Here there are 3 orbitals. So total 4 orbitals, then times 2, 8 electrons. So apply the same concept for n equal to 3 and n equal to 4. So if you notice, right, we have to list down one by one. When L equal to 0, what is the shape or what is the subshell? And then what is the n value? And then what is the s value? And then there are how many orbitals? We have to list down one by one in order to get the number of electrons. If you try to apply the formula 2n square, you check 3 to the power of 2, 9. 9 times 2 is 18. Yes, total number of electrons is 18. How about this one? 4, 2, 16. 16 times 2, yes, 32. So, but you have to know why there are 32 electrons. So check for here. Because all the number of orbital is depends the L value. And then we sum up the L value times 2, then we'll get it. So here 1 orbital, 3 orbital, 5 orbital, and then 7 orbitals. So sum up 16 orbitals times 2, 32 electrons. Let's try some question to test your understanding. So the first question is related with, are the following quantum number combination allowed? If not, show 2 ways to correct them. So a set of quantum number is given, and then check allowed or not allowed. How about this one? Which of the following orbital do not exceed? Explain. So a subshell is given and then ask, is it allowed or not allowed? Actually, these two questions is testing your understanding about the principal quantum number NLMS. So for this case, n equal to L1, L equal to 0, M equal to -1. So it's not allowed. The problem is over here. Because right, when n equal to 1, L equal to 0, and then the M value not supposed is -1, but is 0. So okay, it's not allowed, and then explain why. Suppose N1, L0, M equal to 0. Or we change the principal quantum number, become N equal to 2, L equal to 1, and then M equal to -1. I think mostly students will answer this one. Okay, how about this one? 1p, allowed or not allowed? N equal to 1, L equal to 1 is not allowed because p represent L equal to 1. Why? Because when N equal to 1, possible value of L only 0. 1 minus 1, 0. So 1s orbital exit, but 1p orbital do not exit. Clear? Next question. Okay, list all possible subshell and number of orbital associated with the principal quantum number n equal to 6. So n minus 1 equal to 5. So meaning that the possibility for the L value is 5, 4, 3, 2, 1, 0. So when L equal to 0 is 6s subshell, L equal to 1, 6p subshell, 2, 6d, 3, 6f, 4, 6g, and then 5, 6h. Then to check, when L equal to 0, M equal to 1, so 1 orbital. This one, M equal to -1, 0, +1, 3 orbital. For this one, -2 until +2, 5 orbital. For this one, -3 pass through 0 until +3, so 7 orbitals. This is -4 pass through 0 until +4, there are 9 orbitals. And then when L equal to 5, so M equal to -5, -4, -3, -2, -1, 0, +1, +2, +3, +4, +5. Total 11 orbitals. Since the question wants all number of orbitals, we will sum up. The answer is 36 orbitals. Okay, let's check for this question. Write the 4 quantum number. Okay, 4 quantum number actually is equal to set of quantum number for an electron in a 3s orbital. So you can state first, n equal to 3, L equal to 0 because s orbital, L equal to 0, M equal to 0. And then the possible for s value is -half or +half. This is stating, list down the possible NLMS value. But the question 1 for now quantum number actually is equal to one set of quantum number. So you have to write as n, n, m, s bracket. So the answer 300 +half bracket or 300 -half. So that's all for today. Don't forget to follow my IG at ChemiComSL. Subscribe, like and share my YouTube channel ChemiComSL, and follow my Facebook ChemiComShirley. Hope you all learned something. Thank you.